by the ideal generated by this function W. So this is the ring of homogeneous polynomials on W. Right. So, so starting from this data, I will define two categories. They're both of algebraic nature. The first of them will describe coherent sheaves, or if you want a little smaller set, vector bundles on Y. And it's more or less a rather classical Serre correspondence between graded modules and sheaves on projective varieties. So we know there is a statement that's originally due to Serre that was discovered at the very beginning of algebraic geometry. It says that sheaves on Y correspond to graded modules over SW up to finite dimensional modules. So in Hartshorne's book, you have this Proch construction for graded modules, and there is a statement that sometimes graded modules give the same sheaf if they differ only infinitely many degrees. So this is a non-statement, but I want to emphasize where it is coming from because it will be important to us later. So from the same polynomial, we could consider so Cy, which is a fine cone over Y, and this is the zero set, but now it would be sitting in Cn plus 1. Right. So obviously we could say that Y is this affine cone without the origin, and then you mod out by the natural action of C star. And I want to say that in this description, so this description corresponds to this description. So first of all, if you just wanted to consider sheaves of vector bundles on the affine cone, so then obviously you would look at modules over the ring of functions here. Okay. Now, if you if you want to throw out 0, so this is some operation. Basically, this corresponds to saying that we want to kill finite dimensional modules because they correspond to sheaves sitting at the origin, and you want to get rid of them. And then, since you're taking quotient by C star, so this corresponds to graded things. So this is basically a statement saying that modules on the quotient are equivariant sheaves or equivariant vector bundles on this original space, and so C star corresponds to grading. Okay. But for the statement that I need to formulate, just the category of sheaves, or if you want the set of sheaves, is not enough by itself. One needs to do certain further operation with it. And the operation, there is a comparison due to Makai, who's it's more of a poetic comparison, not a mathematical statement. But he says that you can think of vector bundles on a variety as being, in some sense, similar to smooth functions on a flat space, for instance. And then there is a certain operation that corresponds to passing from smooth functions to L2 of x. So there are some functions which are not smooth, but they're generalized, some distribution sitting somewhere. And then when you approximate them by smooth functions, you sort of get to a different space. Okay, so here's this. And it's an informal definition. We're talking about derived category. And in this case, in this particular situation, we could say that we are taking at first complexes of graded SW modules, and the complexes would be like that. And they're finite complexes. And let's say also finitely generated modules. And there are, obviously, if we have two such things, then we can consider morphism between them. Just commutative diagrams like that. But we want to say that two complexes are the same if, well, we want to describe two situations. In both of them, we'll think of complexes as being the same. In the first situation, we say that, so if this is, this arrow is alpha 0, alpha 1, alpha minus 1. So in the first situation, we say that a kernel of alpha I and co-kernel of alpha I are finite dimensional. Okay, so this corresponds to this operation of disregarding finite dimensional objects, thinking that they're simply equal to 0. And then the second situation in which we identify such complexes is when alpha I induce isomorphism on cohomology. So for complexes, we assume d squared equals 0. We take kernel of this arrow modified by the image of the previous. And so if alphas induce isomorphisms, then we identify corresponding things. So this is a very approximate definition. There, if with technicalities, there is I guess you can go to standard sources, but even by now there are some people who are not completely satisfied with how derived categories are defined. They say there must be something slightly better. Anyway, so this is again some sort of category that you attach to something similar you can attach to any algebraic variety. And again, the comparison that if you think of vector bundles as being similar to smooth functions, then this is something similar to L2. And right, so what is a second category involved? So D, B, singularity W. So this is, again, we start with the same thing, but in one, replace finite dimensional by the word projective modules. So projective is a direct summand of a free module, and geometrically it corresponds to vector bundles. Right. So this is called the category of singularity of W, and so let me just also mention, before I explain why someone would care about these things. So in this case, we start with complexes of finitely generated modules, and then we kill complexes of projective modules. And we look at the quotient in some sense. And so, for any variety, I'll say y, we can define dB y. So this is complexes of coherent sheaves up to quasi-isomorphism. And quasi-isomorphism is by definition, such a map of complexes which induces isomorphism on cohomology. So we declare such maps as invertible, although on complexes you can't really find an inverse. And dB, the singularity category of phi. So this is will be complexes of coherent sheaves again modular complexes of vector bundles. So here the same line means different things. Here we say that quasi-isomorphisms are invertible. Here we say that complexes of vector bundles, we force them to be zero in such a thing. We're looking at such a quotient. Now, what does the second definition have to do with singularities at all?
That's no grading, right?
Sorry?
Is there grading?
Well, in this case, if you're looking just at a variety, then there is no a priori grading. So in our case, I was interpreting everything in terms of modules. So there was a graded ring, and I wanted graded modules. And also on this side, also there was grading. So in the talk, I will be sometimes forgetting this issue of grading just to make things look simple, and then at some moment it will jump out where you do have to remember that when you're working with this particular ring, modules should be graded. Right? And here, right, okay, so basically also in general, grading can come up here if there is a C star action on these varieties, and then it would make sense to try to impose in addition. Okay.
In the top case, it's a cause, so you have a grade.
Yeah. All right. So why care about this singular derived category? So why dBc?
Sorry, can you explain one more time what you mean by quotient complex about this?
Well, it's a strange operation. Another metaphor, when you're thinking about derived categories or categories, you can think of them as rings. For rings, there is operation taking quotient by ideal. So this is somehow a similar operation. So we have this set of objects, and then those which come from complexes of vector bundles, we just declare to be zero. So this is an informal definition. A formal definition is would basically say that you keep the same objects, but then you introduce more morphisms in this category, and you declare this type of objects to be isomorphic to zero. And so it really is equivalent to saying that you're killing them, and you're trying to basically you identify two complexes of coherent sheaves if there is a map between them such that kernel and co-kernel are this. And then you can generate equivalence relation by such things.
Okay. Is it localization?
Huh? Yeah, there is construction localization of or quotients of categories, and so this is a particular case. So this is a right.
But is it just from your definition, but replacing finite dimension projective?
Is it clear?
Yes, I just want to know. That's the first line is your definition, and the last line is.
I'm at this moment. Yeah, at this moment, I'm not saying that these two are the same. In fact, I'm saying it's just a similar definition for any variety. So this is basically a definition which starts from a graded algebra. This is a definition, similar definition that starts from a variety. I'm not identifying them. In fact, I will use this definition but apply it to something else. So we'll see. Okay, so why the singular derived category? And it's easier to explain it in this definition. So assume Y is smooth, F a coherent sheaf. So we assume a coherent sheaf is obviously an example of a complex. You just put zeros in all non-zero spots. So then a coherent sheaf in a smooth case admits a projective resolution. So for sheaves, you can always start writing some projective resolution, but the big deal is to make sure that it will, at some finite step, it should actually end. Okay? So for smooth varieties, you know that for every sheaf there is such a resolution, and then for singular varieties, you know that there will be you are able to write a sheaf for which there is no such resolution. So this is somehow testing smoothness, and you can rewrite the same resolution in the following way. So you take this complex that has only F, and you can cook up obvious arrows. And so this is a map of complexes that induces isomorphism and cohomology. There is no cohomology on this level, and there is cohomology, which is F on this level. So this is quasi-isomorphism. Now, when you pass to derived category, you've declared that this becomes an isomorphism, and also you've declared that this is a complex that you're killing. You're finishing it off. You declare it's equal to 0. So it means that F itself will disappear in the quotient. So F is isomorphic to the 0 sheaf in dB sing of Y. And this is under the assumption that Y is smooth. And so dB sing of Y is trivial. Right, so in general, such things were studied. The algebraic version actually appeared quite some time ago, but it was in representation theory of algebras, not related to geometry in any obvious way. In geometric setting, so dB sing Y studied by Orlov, and a little later it was studied by Krause. And so a statement, again, which I will write only approximately, is that dB sing of X is equal to, well, I want to make an assumption that explains, see, suppose X is a variety with isolated singularities, singular points P1 up to Pk, and then this singularity category will just split into direct sum of just local versions of dB sing at Pi. So local versions in the sense that you can look at modules over the local ring of that point. So in general, this, for instance, if you pass to open subset of X which contains all singularities and you throw in out just smooth points, then such a thing doesn't change at all. So it's really, this is a category that's measuring precisely the information about singularities of X. And so there is also, just to illustrate, there is an expected statement. So last time I've checked, it wasn't really written down, so it's still a conjecture. That say if X has, so is a hypersurface in, let's say, Cn+1, given by vanishing of polynomial W with isolated singular point P, which we assume to be the origin. We can always do that by shifting coordinates. In this statement, it doesn't have to be. So homogeneous is only needed when you want to work with graded versions, and so. Okay, so then there is this the singular category of X, and categories, in some sense, as I said, they are similar to rings. In rings, you can multiply elements. In categories, you can compose different arrows whenever end of one arrow matches the beginning of another arrow. So in some sense, categories can be thought of as generalizations of rings. If you consider a Abelian category with a single object, you honestly get just a ring. So for rings, there are homological invariants like Hochschild homology and cyclic homology. And so if you, so this, maybe a lower star. So this is Hochschild homology. And a reference for Hochschild homology of categories of this type is works by Bernard Keller. On his website, he has very nice overviews for homology theories on categories. So this is expected to be the Jacobian ring of P, which by definition is just, so you start with the polynomial ring of functions here, x, and you mod out by the ideal generated by W, but also by its partial derivatives. So if we were trying to deal with if say P was actually a smooth point, then this would be equal to 0. So this is one ring that measures complexity of the singularity, and in simplest cases, when you have, say, simplest if you have Morse number, so there's some information, sorry, Miller number. You can just calculate by computing dimension of this, and so.
In here, actually, we are looking at Hochschild homology as a ring.
Well, Hochschild homology originally are applied to rings, but this is a category, and you think of a category as some generalized ring. The construction of Hochschild homology extends from rings to categories. So if you apply it to this category, it's expected that one should be getting this.
Yeah, so as a ring or as a ring?
No, I don't think so. No. It's there might be more to the. You might need some. It's rather similar to the situation with usual derived category when you're applying appropriate functors and you can recover cohomology vector space from the derived category, but you're not able to recover the ring structure because there are examples when derived categories are the same but ring structures are different. So not, I think, just as a vector space.
So what do you expect when T has non-isolated?
I'm not sure how to formulate Jacobian ring for non-isolated singularity, but I think that all classical information that make sense holomorphically. I'm not talking about not necessarily vanishing cycles, but things which any invariants that you can cook up by playing with polynomials of this nature, I think they should be hidden here. I think it's a stronger invariant. Yeah, and so just maybe I should have said in the beginning so that these singular derived categories are, in physics terms, are called B-model Landau-Ginzburg models. So it's the B side, and Victor was talking about A side. So it's in A side you'll sort of view, you look at maybe symplectic information and things like vanishing cycles, and here this is a purely algebraic or maybe holomorphic game. So there is never C-infinity geometry coming into the story. All right, but this is basically just to give a feeling of why this category could be interesting and why people care about it. So here's a statement that was originally proved by Orlov. And it says that we go back to the situation where W was homogeneous because we wanted to define hypersurface in Pn, and say that if degree of W is equal to n plus 1, then the derived category of sheaves of vector bundles on Y is equivalent to the singularity category of this function W that I defined originally. And this, maybe there should be notation for graded, so with GR somewhere, but it will make notation look too heavy. Now, so this is precisely the situation when the corresponding hypersurface in projective space is Calabi-Yau, when it has a non-vanishing, nowhere vanishing top degree differential form. And so it means that Y sitting inside Pn is Calabi-Yau. Its canonical bundle is trivial. So obviously, when n is when the degree is smaller than this, then we're dealing with a Fano hypersurface, and when it gets larger, we get anti-Fano. And then, actually, more general result of Orlov was saying that in these other cases, so when the degree is smaller, then you have inclusion in one direction, and when it gets larger, you have inclusion in the other direction. Although don't remember quite which goes with which, right? So the categories are related in all degrees, but they are equivalent precisely in this condition. So our joint work with Jeremy Picharic started with this attempt to replace Pn by a toric variety, such as, say, product of projective spaces, or there is this Hirzebruch surface F1, etc. And Y by a Calabi-Yau complete intersection of hypersurfaces. Okay. So it turned out that although a lot of things are known about toric varieties, there is one part of our original proof of Orlov which is purely algebraic. There is one part which we couldn't really generalize to toric varieties, and so couldn't generalize the algebraic proof of Orlov. So he uses the following functor. So if you start with F, which is a sheaf or a bundle, his paper, he considers a certain functor which sends this sheaf to a complex of graded modules, graded SW modules, with ith cohomology, which is given by direct sum of hi y f twisted by n. So y is embedded into a projective space which has a standard line bundle of n, and this is a tensor product, and this is direct sum is taken over n greater or equal to 0. Or you could write greater or equal to 1 or 2, any of the favorite spots. But what the statement that he's using is that so this thing is always a finitely generated module over SW. So the proof depends on this. Now for H0, this is an easy statement. For H0, you could just take, let's take direct sum over all integers. Then we know for n negative enough, it will vanish anyway. So this is all results of Serre about sheaves on projective spaces. But if you go to higher cohomology, especially to top cohomology, the situation reverses. For very negative n, you have non-trivial cohomology groups, and then for positive, they vanish by this vanishing theorem. So this restriction on n is a way of really making it finitely generated. So top dimensional cohomology, if you consider all twists over integers, without this condition, it wouldn't be finitely generated. And now, for general toric P, we would have to write direct sum of cohomology on hypersurface of complete intersection F tensored by L, where L runs through all possible line bundles in the group of line bundles on P, but it's hard to formulate the condition that n is greater or equal to 0, which ensures that this direct sum is somehow finitely generated, well behaved in some sense. That will become clear. I'm mentioning it because this seems to be an important problem in toric geometry. Just say, never mind the hypersurface. Let's just assume we have toric variety, and you start having a sheaf. Then, how do you do this truncation for higher degree cohomology to ensure that they are finitely generated? Yeah. Again, I will tell later over which ring. Right. So there were some powerful results in this direction obtained by Eisenbart around, with some co-authors around 2003, maybe 2005. And there were some results by McLagan and Smith, some finiteness properties of cohomology on toric varieties. Anyway, and we'll actually later we'll see that it wasn't by accident that there is a problem there, that the answer in general needs a new factor which isn't present in the case of Pn. Now, so we, instead of pushing the algebraic side, we try to find a geometric restatement. Finding a geometric restatement. So this geometric restatement is based on a theorem by Isik Umut, who is the greatest student of Tony Pantev, and the statement, and I'm writing a particular case of his result, which is simpler than what he's proving, But suppose again we start with a global section of anti-canonical bundle on P, where P is just some smooth projective variety. So the fact that it's a section of anti-canonical bundle means that if you look at the zero set, then it's Calabi-Yau, and to make sense out of it in terms of manifolds, we assume also smooth. Now, consider the function let me just write and then I'll explain the notation. So omega will be a total space of canonical bundle, and the function goes into C. So total space of K. I want to think of this as a line bundle, and I want to think of this as a manifold or a smooth variety. And so function W tilde defined by the regional W. Okay, so what do I mean? Well, if we're taking a point here, it's given by a point in the regional P, and also a vector in the canonical bundle. But once we specified this section, we can just pair the vector in the canonical bundle and our section by getting a number. And so we get this. So this is a function which is a fiber-wise linear function. Fiber-wise linear function on omega. Right? Then, the derived category of sheaves on Y is equivalent to derived category, again, singular derived category of W tilde inverse of 0, the 0 level of this function. Okay. So what is the idea of proof? So the idea of proof is, well, the first step is that you replace Y by what is called Koszul resolution of a structure sheaf. So you have the canonical bundle on P, you map it to the structure sheaf on P. The map is given by multiplication by the section that we're using, and you view this as a sheaf of graded algebras with a differential. So the algebra structure is that here you use usual multiplication, then O acts on K in a natural way, and then you assume that this has square 0. So it's really naive and very easy algebra structure. And then, as a second step, you would say that dB Y is equivalent to dB, so will be differential graded modules over this differential gradient algebra. So let me just give it a name, K curly, and I'm just writing this. Right, so it's just, first of all, it's graded modules, but then also they should have a differential such that which agrees with this differential in the sense of Leibniz rule. Huh? Sorry? Differential?
Oh, okay.
Yeah. Differential graded modules over the sheaf of algebras. Okay? So this is really an algebraic statement. Whenever you have a differential gradient algebra and you have its cohomology, so under some nice conditions, the derived categories are the same. But the usual categories are not the same. So this is the first reason why we need DB and we're not working just with modules. So if you have quasi-isomorphic DG algebras, then derived categories are the same, but not necessarily modules are the same. So this is the first statement. So this is how we pass from Y to something that lives on the whole of P. And then next we use a generalized form of there is in algebra there is an equivalence. If you're looking at modules over exterior algebra, then they turn out to be equivalent to modules over the symmetric algebra of the dual vector space. So just for reference, this is called BGG correspondence. And you say that instead of a vector space, you take just rank 1 sheaf, which is K. So lambda 1 of V, which is V itself. So that corresponds to K, and lambda 0 of V corresponds to O. So then you're able to pass from modules over this algebra to, okay, so let's just write that sim V star. What is it? Well, this is the symmetric algebra over K dual, because you're dualizing, but these can be thought of as functions on omega. Okay. So there is a lot I'm omitting here. I'm omitting completely what to do, how this statement should take into account this multiplication by W, and why on this side W should pop up. But this is really where the work needs to be done. But at least the concept is quite reasonable that such a thing should. All right, so now let me just write a restatement So using this theorem that I just outlined, how can we reinterpret the result of Orlov? So this converts Orlov's theorem into a statement that dB, the singular category of omega inverse of 0, is equivalent to this algebraic singular category that I first defined using graded as W modules. So basically, there used to be the usual derived category of some hypersurface, and Orlov's theorem just allows to show this. But now, if we look at now both sides at least look rather similar, but if we stare carefully, we see that W tilde is a function on the canonical bundle of Pn with values in C. What was W? It was function on C n plus 1 with values in C. So these things aren't quite the same space. So the function is really more or less the same because it's given by a degree n plus 1 polynomial. It's just you use this polynomial in different ways to obtain functions on different spaces. Now, how do we relate one to another? And this is where the actual geometry kicks in. So you first observe that there is a map from the canonical bundle of the projective space into Cn plus 1 mod Zn plus 1. So if you calculate these things with zero section can be contracted into a point. So zero section is sort of a divisor with negative normal bundle. You can contract it to a single point. Another explanation that this is equal to the spectrum of the globally defined regular functions on the canonical bundle. So this again, contracts the zero section to the singular point of Cn plus 1 mod Zn plus 1, and its isomorphism as elsewhere. Okay, so this is in different terms. You can start with the singular space and say that this is one example of its crampant resolution. So this is a resolution, and it actually in addition has trivial canonical class. So what? Okay, what else you can do? Now here's the effects of grading that I'm not going to go into, but there is a second resolution, and resolution in a slightly different sense. So I want to, okay, what is this? You can say this is a variety with a finite group action. You can construct a quotient which also will be a variety. But you can construct a quotient in a different sense, in a sense of what is called orbifolds or Deligne-Mumford stacks, depending on whether you're coming from differential geometry side or algebraic geometry side. So this is quotient as orbifold or Deligne-Mumford stack. So what is it? Well, it's just stacks. Orbifolds are some generalization of the usual objects. And let me just illustrate the difference between them. It won't be a definition of what a stack is, but I want to illustrate the difference between those by saying that what are vector bundles on Cn plus 1, Zn plus 1 with these square brackets. So if you find a definition of the stack quotient or orbifold quotient and unwind what vector bundles on this are, so these are exactly equal to Zn plus 1 equivariant vector bundles on Cn plus 1. More or less by definition of the thing involved. Now, what are bundles on the honest variety quotient? Not quite the same thing, because bundles on Cn plus 1 mod Zn plus 1 will be actually equivariant bundles on Cn plus 1 such that Zn plus 1 acts trivially on the fiber at 0. So in a sense, in the orbifold situation, we have more bundles than we have in the honest variety quotient situation. And this is why we say that this is at least a resolution. So in some sense, you're adding something. So in this, for instance, you could say you're adding vector bundles, and also you can treat this as if it were a smooth space. And so now there is, in such a situation, we have what is called Makai correspondence. So Makai correspondence will say that the derived category of omega of the canonical bundle of Pn is equivalent to the derived category of Cn plus 1 mod Zn plus 1, which more or less by definition is the same as derived category, equivariant derived category of the flat space Cn plus 1. So that means you look at sheaves together with the Zn plus 1 action. Right. So now, why can I write this? Well, first of all, one needs to say that this is interpretation of Makai correspondence, which is developed by Bridgeland, King, and Reed. So they actually considered the situation when there is a group acting, a subgroup of SL3 naturally acting on C3. And you take a quotient in a sense of varieties and then take a Crepant resolution. So they proved it in this case. This situation is similar to it. It's not quite covered by the result, but it's also not too hard to establish it. All right, so fine. Now, if we compare what's written here and what's written here, well, at least now the spaces are, we could relate spaces to each other, but then there are functions which are standing here. So this equivalence is not exactly as this equivalence because there are functions involved. So to get this statement, and which is what we need.
Explain why you get naturally that Gn plus 1 action.
Zn plus 1 action. It's just it's a trivial. It's just a scalar multiplication. It's just on x1, sorry, x0, xn it's just equal to x0 zeta xn. And so since if you're taking it in Zn plus 1, then this linear transformation has trivial determinant. So it preserves canonical class. And you could say that this orbifold is Calabi-Yau. It's
But how can I see such action on the space of a global vector field over Pn?
on Pn, you don't see it. So what you have really is so in both spaces you have C star action.
Yes.
But in a sense, it's a sort of canonical class of Pn is O of minus n minus 1. And so the result is that when you start looking at, so the two C star actions in some sense they differ precisely. They both descend to this quotient, but they differ precisely by this raising of. And if you look at the grading, which is the thing I've been suppressing all the way throughout, so the Z graded modules on this side would correspond to taking into account this action.
I was confused with omega,
omega
1.
Right. No. Oh, well, omega. Sorry, I should be writing omega n. Right. So this is the explanation why why the group is such. And we'll actually use this a little later when we try to generalize it.
Can you explain one more time from this omega n to this quotient C? This arrow you have to use contraction.
Oh, yeah. So the arrow that I just raised was, so you have a zero section here. Zero section has a negative normal bundle. And by some standard results, you can contract it to a single point. There is a birational morphism onto what in this case turns out to be a fine variety, which contracts the zero section, and away from zero section, it's an isomorphism. And the target of this map turns out to be spectrum of ring of globally defined regular functions. So all these functions, they would vanish along Pn. So the value, basically you take all regular functions that are on Pn, you calculate their values, and the values live in the corresponding affine space. And it turns out that values of all regular functions, they vanish on this zero section of Pn. And so the whole Pn, this Pn disappears into a single point. Elsewhere, regular functions separate points. And so there will be, so you're really just shrinking down just one piece. Right. So up to now, this was just use of what other people did, except this equivalence, which is some sort of exercise in Makai correspondence. But now we need to get from the picture without any functions, without any W's, to the picture that does have W's. And so we prove the following theorem for this case. Just a second. Yes. So theorem. Suppose that so you have x and you have y. Both of them are resolutions of the same variety. So two resolutions of Z, and maybe they're resolutions in a sense of orbifolds. Maybe orbifolds. So maybe they're smooth orbifolds. And suppose there is a complex of vector bundles F with dot on their product such that dbx dby, so the functor from one category into another, which is obtained by, first you pull back, so you have pi x going to x, and you have pi y going to y. And suppose what you do is you pull back G, you tensor it with the complex of vector bundles, and then direct image onto y. And suppose this is an equivalence. And so in all nice situations, equivalences are given by such a complex of vector bundles. If x, y, and z are projective, this is actually a theorem proved by Orlov. If they're not projective, one has to be even careful to make sure that this is well defined. And this is why I'm writing this situation. So you sort of expect that the cohomology of this complex sits on the fiber product of x and y over z. And then properness of these two maps helps you to define direct image. So these are direct images in the sense of derived categories. So suppose you start with a situation. So you have two birational smooth varieties and with derived categories equivalent. And so this transformation is called Fourier-Makai transform. So it's similar to Fourier transform functions on one torus to functions on. Right. So